Good morning, good evening, good afternoon. This is Dr. Garais, MED110, 6DAX, term 3. And today is July 22nd, Wednesday. Now, just a real quick public service announcement, and I'll also be mentioning this as well on announcements. By the end of week 10, and what I mean by the end of Saturday, 12 noon, I have to hand in all grades. And again, if you miss something, please submit it because some credit is better than zeros. And some of you already taken advantage of that. And those of you who've never done a lab with me, you have to submit a term paper instead. And the instructions are again and also in announcements. If you look at your lesson 9 at the end of lesson 9, this final exam is due by that 12 noon. So, and what I mean by 12 noon is starting 11 a.m., I'm going to start looking at grades, start doing calculations and everything, because by 12 noon, the university wants the grades. And the posting of grades is crazy important because many of you are applying to the School of Nursing and have active applications, and some of you have pending decisions. So please don't wait till do not wait till the last minute. And also, it also affects your financial aid. So please don't wait to the last minute, and especially grade changes are detrimental to your financial aid. So it's best to get everything done, and that's what week 10 is about. So we won't have any Zoom lectures next week. Next week is just a catch up for all those who need it, and final exam for those of you who are ahead of the game if you want to finish that up early. All right, so let's now go to what's our topic for today. And again, it's continuation of homeostasis, and we're going to talk about buffer systems. Now, this chapter is important, especially those of you who are wanting to go on to nursing. This is one of the high value targets for NCLEX, and the basis of this stuff is the basis for arterial blood gas, which a nurse should be able to read and interpret. I'll also be putting up a link to how to interpret an arterial blood gas. I'm not going to go into that here, but you really should take a look at that and then apply your knowledge of what this stuff is. So the first thing we have to define is, if we haven't defined it already, is what is acid base? Why is my computer freezing up? All right, move this out of the way. What is acid base? So let's look at acids. And what does pH mean? So pH is a scale. It's based on a logarithmic scale. And I think if we didn't talk about this before, if we talked about this before, I'm saying this will be a nice review. But if you've never seen this before, this is pretty neat stuff. Now, when you look at this scale, right, you have a scale of essentially 1 through 14, and that's your pH scale. Now, pH actually means the negative log of, and it looks something like this. Why is everything so slow? Okay. What pH actually means is the negative log of the concentration of hydrogen ion. Okay. And then let me like this plus this. Now, what does that mean in English? It's a scale from 1 to 14. And in the middle of that scale is a 7. Where should we be? We should be, human beings are around 7.2 to 7.4. So it's a balance. So what does this mean? Anything closer to 1 has a lot of hydrogen ion. Okay, so on this side. Anything closer to 14 has a lot of hydroxide ion. Now, if it's too much, now either way, if we recall from our week 2 lecture, that these little extra pluses and minuses, this one here, right, and this one here, that means that substance is reactive. And if there's a lot of H pluses, it's a very, very strong acid. So it's closer to 1. There's a lot of OH minuses. It's a very strong base or alkaline, which is closer to pH 14. Now, pH is one of those things that we monitor in our patient because metabolically or chemically, the patient needs to be where? In the middle. So if they're either on either side, either closer to 14 or closer to 1, that's not a good thing. And it'll ruin a whole bunch of chemical processes. So being super acidic is not good. Being super basic, also known as alkaline, that is also not good. And just like homeostasis itself, where do we always need to be? We always need to be in the middle around. And for a physiologic pH is what? 7.2 to 7.4, something like that. So if we look at here, remember we had H plus over here, OH minus over here. Guess what? If I put H plus and OH minus together, I get H2O. It's water, which is you, which is more than 2/3 of you. So that makes sense. So the majority of you are water, so you should be where? In the middle. And then you look at certain things that have a low pH. They're starting to get progressively acidic. Orange juice here, right? Certain fruits, grapes, and tomatoes. But then all the way at pH 1, that's hydrochloric acid, which is your stomach acid. If you recall, that's what we need to kill a ton of bacteria and or foreign body that gets into our food. Okay, so that means that substance, hydrochloric acid, has a lot of H pluses, and it means it's highly reactive. Okay, now we look on the other side. You have eggs, baking soda, like ammonia, bleach. That stuff is highly basic or highly alkaline. And again, this stuff's highly reactive. Don't put bleach on your skin. Don't ingest bleach. Don't ingest oven cleaner. Oven cleaner is all the way at this end. Oven cleaner is highly basic. Okay, so you could see these things are toxic to human beings because it's on the extreme part of the spectrum of pH. So now you know exactly when we look at pH, what pH actually means. It means the negative log of the concentration of the hydrogen ion. Okay, so knowing that, how do let's look at how do we control it? Okay, so let's look at this. Now, we have these things called buffers in our body. And the buffer system is a system of chemicals that are they're mild acids or mild bases. And that makes sense because if we look at our spectrum here, right? Let's make this 1 to 14, make this 7, make this a little bit further out. So the 7.2, that's where we need to be, in the middle, right? And that's our hydrogen ion, that's all the way out here. okay? Now, the way a buffer system works is, and I'm gonna show that video in a second, is let's say you have a pH of like 8.5. That means you're what? You're a little bit off center. So what was your body gonna do? You're more towards the basic or the alkaline over here, right? Let's write down acid. So over here, this is your acidic. Over here, your basic, also known as alkaline. So now you know what a battery is. Battery is what? Alkaline, and it also has acid. And we'll talk about that in another class, how you're actually a battery. Human beings are just batteries. A very complicated battery, but a battery nevertheless. So if you're here, a little bit basic, a little alkaline, there'll be a buffer system of a weak acid to do what? Slowly move you back here. Now, if you're acidic, let's say pH 5.9 or so, there's a series of weak bases that will pull you in this direction. And isn't that the definition of homeostasis? If I'm out of balance, something will occur to put me back into balance. And that is what the buffer system is. So that's the general overview. So let's look at this video.
Buffer systems play important roles in nature and in laboratory settings. In nature, they offer protection to living organisms, while in labs, they're used to create an environment with a stable pH. By definition, a buffer system is a solution that resists a change in pH when acids or bases are added. Acidic solutions contain high concentrations of hydrogen ions and have pH values less than 7. Basic solutions contain high concentrations of hydroxide ions and have pH values greater than 7. Neutral solutions contain equal concentrations of hydrogen and hydroxide ions and have a pH of 7. Buffer solutions can have any pH. What makes them special is that they keep that pH even when acids or bases are added to them. Our blood is a buffer system that keeps pH between 7.35 and 7.45.
Oh, my bad.
It is important that the pH does not stray too far from this range. Blood that is too acidic or basic can damage bodily tissues. Seawater is also a buffer. The average pH of ocean water is 8.4. The buffering ability of ocean water protects sea life from the corrosive effects of acids and bases. A buffer system can be made of a weak acid and its salt, or a weak base and its salt. A classic example of a weak acid-based buffer is acetic acid and sodium acetate. A common weak-based buffer is made of ammonia and ammonium chloride. Chemists can prepare buffer systems to be almost any pH they want. The pH of the prepared buffer will depend on the relative strength of the chemical contents. Sensitive tools like pH probes that are exposed to acids and bases are often stored in buffer solutions. It's critical that buffers are made from weak components.
Actually, just as a side note, and being a chemist and also a lab rat for many years, we don't store them in, we store them in double distilled water so that the pH would be around 7. So the the pH meter is always calibrated to dead even, unless it's for something specific. And if you saw the end of that probe, it's made out of glass usually, and it's quite delicate.
Acids, for example, don't release large amounts of hydrogen ions in solutions like strong acids. Rather, the hydrogen ion prefers to stick to the rest of the compound, known as the conjugate base. Here's a
all right. Now they're getting a
representing.
Now they're gonna get into a little bit more chemistry, but you could see what a buffer system does. It keeps you in the middle, and either by adding a weak acid if you're too basic, or a weak base if you're too acidic, to push you in either direction. So if I'm over here, right, in the acidic world, the buffer system will add hydroxide ion. Now, let's go back to our little chart here, and let me show you some buffer systems that your body has. And they mentioned acetic acid is one of them. One of your solutions that maybe you heard on TV or maybe you saw at work, right? Maybe you heard of Ringer's lactate. What's lactate is lactic acid. So Ringer's lactate, that solution that we put in your IV, is a buffer. So if I'm a little bit basic, it's going to pull me towards the acidic world. And maybe you heard of this, which is sodium bicarb. Bicarb for short, but bicarbonate. And this is NaHCO3. And then the 3 is subscript. So sodium bicarbonate is a weak base. So if my patient is acidic, I give my patient sodium bicarb, what's it going to do? It's going to pull me towards the middle. Another thing that we can also do is I could give you things like buttermilk. I could give you things like orange juice or cranberry juice to make your blood acidic. Okay. So diet also can dictate pH. And that's why when you go to the hospital and you eat that so-called food, I always remind the patient that's not food, that we treat it more like drugs. We treat it more like part of your therapy. So the function of the food in the hospital is not to taste good. And it does that function rather well. The function is to get your pH normalized, to get your homeostasis and your metabolism normalized. And that they try to make it as tasty as possible, but they can't. Unlike a restaurant's function is to try to make it as tasty as possible by putting as much salt, as much sugar, and as much fat as they possibly can into that meal. Dietetics in the hospital, they can't do that. And you could now see why. Okay, so this is this is some classic classic ways that your body maintains your pH or your acid slash base levels. So let's now go to, so that's a buffer system. Now, it goes, there are other systems that regulate acid and base. And the next one is respiratory, okay? Now, how does respiratory regulate your acid base? Well, remember when it goes, when we're breathing, we want to exchange oxygen for carbon dioxide. Well, the best way to put it is that when you breathe out carbon dioxide, you also breathe out acid in the form of hydrogen ions, okay? And that makes sense because when you're working out, right, or when you're doing something strenuous, your muscles start breaking down the glucose and uses up the ATP. Well, one of the byproducts is acid in the form of lactic acid. That's the reason why when you go running and you haven't worked out in a while, you start cramping up and muscles start aching and start hurting, right? Especially if you're not used to that workout. And that's because of the acid buildup. Now, what also happens when you work out? If you're working out right and you're performing strenuous activity, what's going to happen to your breathing? Your breathing will increase. So there'll be an increase in your respiratory rate, okay, RR, respiratory rate, to get rid of that H plus into your system. So that's one way that your body can bring your acidic pH back to, and let me write here, 7.35, my bad. It's 7.35 to 7.45 according to the lecture. I thought it was 2.5 to 3.5. Silly me. So increase respiratory rate to bring you back. Now, if on that side is, let me push all these over. If increasing my respiratory rate kicks out hydrogen ions, what will happen if my blood is alkaline? The reaction of my body should be what? Decrease respiratory rate. Because if I decrease the respiratory rate, that means I keep hydrogen ions, and then it'll move me back where? Back towards the middle. So what I like to do is, if I have two opposites, I like to memorize one like my life depended on it, and the other one is simply the other one. And my example of like workout physiology, it's easier to remember because lactic acid, buildup of acid in your muscles, you're working out, right? That's why every once in a while in the gym, you always see some guy, usually somebody trying to show off. They're trying to lift as much weight as they can, but they don't breathe, and then they pass out. Because if you don't breathe, your blood will get very acidic, and if your blood gets very acidic, it won't let go of the oxygen off of your red blood cell, and then you pass out. And of course, you're not breathing; you're holding your breath. That's why if you look at Olympic and powerlifters, what are they doing the whole entire process? They are breathing. They're grunting. They're yelling because they want to get rid of that hydrogen ion. They want to get rid of the acid in their carbon dioxide when they exhale, when they breathe, when they push out, and then it'll push their pH back towards the middle where we belong. Okay? Now, knowing this is also a way that we can also control pH via the mechanical ventilator. And the technician, along with the pulmonologist and internal medicine, we do that on a regular basis. That's another tactic that we use. So we can use medical, as you can see here. We could also use the mechanical ventilator or your respiratory as well. Now, let's look at the third item or way that we control acid base, and that's renal regulation of acid base balance. So let's go. Let's get this picture up. Now, we already know that my kidneys have the ability of absorbing and reabsorbing things, throwing out things that it doesn't want. Well, the one neat thing that it can throw out is, let's see, it's a good picture. Where's the one that I use? See, this one's too chemically. I don't want to expose you guys to too many chemicals. I just want you guys to get the overall picture. Here you go. Here's a nice. Remember, we know that the kidneys can chemically throw out, it's a screen essentially, and it can pick and choose through reabsorption and secretion. It can pick and choose what it wants to throw out, okay? So we already learned about buffer systems. We already learned about how respiratory and your CO2 or this PCO2, your partial pressure of carbon dioxide, affects your pH of your body. Well, your kidneys also affect things. So for example, kidneys can do two things. One, it can generate bicarbonate. It can generate bicarbonate by reabsorbing HCO3 and then goes putting that back into the blood. Because if you, well, I don't think you guys had my kidney lecture yet. You get that in anatomy and physiology too. But in the kidney lecture, it filters blood, the kidneys, and then performs these two other vital functions. reabsorption, and secretion. Secretion means it's going to throw out stuff that it forgot to throw out or that it needs to throw out. Reabsorption is it grabs stuff from the urine that it's like a second thought, like a second backup system, like, ooh, I didn't mean to throw that out. So if you're acidic, your kidneys will start secreting hydrogen ion. And then it makes sense. If I secrete hydrogen ions, I get rid of hydrogen ions out of the system, what will I have? It'll push me back towards the middle if I am acidic. Now, if I'm basic, I'm sorry, if I'm acidic, it will throw out hydrogen ion. Now, another thing that it also does is, when I am acidic, is that it's going to create bicarbonate, right? And then, so kidneys create bicarbonate, and then what will happen? We already know that bicarbonate is one of your body's buffer systems. So what will that do? The bicarbonate will then push the pH level back towards the middle. So there's two functions. Now, that's response if your body's acidic. If your body's basic, it'll do the exact opposite. It won't secrete hydrogen ion, and it'll stop reabsorbing bicarbonate. So acid, think what? Your kidneys will throw out hydrogen ion and will keep bicarbonate. But if it's, maybe it's in the picture lower. No, they just assume that it's the exact opposite. But let's say there's too many OH minuses. What will I do? My kidney will chemically retain the hydrogen ion and then will stop making bicarb. So we now see that either situation of being too acidic or too basic is never a good one. And it wreaks havoc on not only your blood, but also your body tissues. Actually, it's one of the many ways we know diagnostically that something severely, not even necessarily severely wrong, but something's wrong. If the pH isn't working. So that's your pH, right? What's this? I never clicked on this. Oh, this is a nice little tutorial. It goes throughout the same things that I've been talking about earlier. Never really clicked on that before, but check it out. It looks nice. But now, why is this? It goes, now we know that we have buffer systems, respiratory reaction, and also renal reaction to what your acid base is. Now let's look at chapter 26.5 in your textbook. What are these things? And these are situations that our body can get into. Metabolic acidosis or metabolic alkalosis. That means the chemistry of our body is off. Respiratory acidosis, respiratory alkalosis. That means our respiratory is off and it's creating an acidic environment or an alkalotic environment. And that makes sense because if I'm breathing too fast or breathing too slow, or the mechanical ventilator is not set right, it's going to create acid, and it's going to create a basic environment. And last but not least, compensatory mechanisms, and that's this stuff. So what will I see? Like if I have acidosis, how will I be breathing, and how will my my kidneys react? So let's look at that 26.5, and we open up the main part, and then you look at your open stacks. And then we go to table of contents, and we scroll down all the way to 26.5. See if I can scroll down faster. 17, 18, 19, 20, 26, 26.5. Okay. Let's look at now. let's look at this, metabolic acidosis. Now, what does that mean? Metabolic, when we look at the word metabolic, ic pertaining to meta, change, bol, growth, I want you to think of the chemistry, okay? So it goes, if I have metabolic acidosis, right, there's something wrong with the chemistry of my body for whatever reason. And odds are it's bicarbonate, right? So that makes sense. If my bicarbonate is messed up, right, I won't have a buffer that'll bring me towards the middle, so I'll stay more acidotic. Now, don't memorize these. You'll learn later that you could pretty much figure a lot of this stuff out. But I want you to get to the basic concept of what metabolic acidosis is. And according to your textbook and according to the National Kidney Association, the most common and it's the most preventable is diabetic ketoacidosis. Now, remember we talked about ketones? If your body thinks that you're running on empty, especially if you're diabetic, the sugar or fuel is not going inside the cell, so your cell thinks you're on empty. And if your cell thinks you're on empty, what will your body make? It'll make ketones. Well, remember I talked about how ketones were neurotoxic? Yes, they're not only neurotoxic, but guess what? They're acidotic, right? And it'll overwhelm your bicarbonate. And if it overwhelms your bicarbonate, you get DKA, which is diabetic ketoacidosis. And that's a bad state of affairs because that is coma ready. Even at relatively low blood sugars, I had a patient who went in coma. Her blood glucose level was like 220, which is horrible, but it's not. I've seen far worse. But she eventually died. So when you think keto acid metabolic, I want you to think it's a chemistry problem, it's a bicarbonate problem, and most common is DKA, diabetic ketoacidosis. Metabolic alkalosis is the exact opposite. So what does that mean? That means I have way too much bicarbonate. So if I have way too much bicarbonate, my pH is going to be pushed greater than 7.35 to 7.45. It'll be on the right side of the spectrum. And most common is usually some sort of GI disturbance. That's the most common because, and if you're like, what do you call that? You're vomiting a lot, you're going to be kicking out a lot of acids. You kick out a lot of acids, or you have severe diarrhea, right? Like excessive use of laxatives, right? Misuse of diuretics. Remember, what does diuretics do? They're water pills. You're kicking out salts. And isn't what an H plus and OH minus, they're metabolites. They're essentially part and parcel of your chemistry and part and parcel of the salts of your body. You start throwing that stuff out. So metabolic alkalosis, the exact opposite, but I want you to think, oh, that's more of a GI problem. Now, respiratory acidosis, right? Of course, they're acidic, and that means they have way too much carbonic acid because, remember, you have way too much CO2. That means my patient is not breathing very well. And that's stuff like COPD, pneumonia, emphysema, because if you're not breathing very well, right, you're retaining a lot of acid, right, H plus, in the form of carbonic acid, okay, because CO2 plus H plus is carbonic acid. Now, respiratory alkalosis is the exact opposite. My patient now is breathing too fast, and that's in the case of hyperventilation, and it could be a whole bunch of things. They could be having an anxiety state. They could be on drugs. Aspirin overdose, because aspirin is salicylic acid, right? But that's respiratory alkalosis secondary to some compensatory mechanism. So when you're thinking respiratory, think respiratory acidosis. My patient isn't breathing very well, not breathing very fast, very low respiratory rate, and that's classic for COPD chronic obstructive pulmonary disease, which includes emphysema and what do you call it, chronic bronchitis. Now, congestive heart failure, that's just a secondary thing that happens to your heart. The main pathology there is the lung issues. So when you hear respiratory, I want you to ask yourself, is my patient breathing very slow or breathing very fast? If it's breathing very slow, it's respiratory acidosis. If they're breathing very fast for whatever reason, that's respiratory alkalosis. Okay? Now, of course, the compensatory mechanisms, we already talked about that, right? If you're acidic, your breathing is going to increase. If you're alkalotic or basic, your breathing is going to decrease. Metabolic compensation, we already talked about what the kidney will do, right? Either kick out hydrogen ion or in the same vein, create bicarbonate. So let us look at, oh boy, my baby's awake. I can hear him. I'm not sure if you guys can hear it. Let's hope someone's taking care of him. Let's see now. Just kidding, my daughter's up there. Let's see. Ooh, let's see the response. Is that the? Oh, okay. Somebody else. All right. Why is it so slow? Where is it? Where is it? There you are. So let's go back to, I always do that. Let's go back to, you know, you'd think after 9 months of doing this stuff, I'd be used to this Mac, but I'm not. Let's now look at, now you know what these disorders are. We already kind of inadvertently talked about the compensatory mechanisms, which are these, right? So now you know what pH is, what pH balancing is, what are compensations and corrections, and what are buffering, right? So now let's go to the actual practical application, which is, and drum roll please, not in the discussion, it's in the lesson. And these are nice videos. Now, it goes in arterial blood gas, okay? So if you look at this, there, watch this, and I think you could look up a better, when it's like this, that means the link doesn't work, but I didn't like this video anyway. But this video here.
Hello and welcome to the 6 Easy Steps to ABG Analysis. In this program, we are going to go through the normal values for blood gases.
Now, of course, for this class, you don't need to know normal values and whatnot, but you know, it's nice to start, especially if you have endeavors for nursing, nice to start memorizing this stuff. Because once you get into your pathology class, they go through this so fast, and because they assume that you already know this lecture that I just went over. So let's look at this.
Values and interpret some blood gases to give you some practice with the major components of an arterial blood gas. So let's go ahead and let's get started. So the 6 steps to ABG analysis are, 1, we're going to look at the pH, then we're going to look at the CO2, the bicarb, and onward. Notice that there's 2 main components that we are assessing when we look at a blood gas. We're assessing both the pH, which tells us about acid-base balance, and we're going to assess the oxygenation status of our patient. So 2 different areas of information that we're getting from arterial blood gases. So the arterial blood gas was drawn from the patient. Now we're going to take a look at the results and try to determine what we can find out about both the acid-base balance and about the oxygenation for this patient. The first step is to look at the pH. When we look at our arterial blood gases and our components, we don't want to talk about these values in terms of them being high or low. Instead, we want to talk about them in terms of being normal, acidotic, or alkalotic. So let's take a look at the first step. We ask, is the pH normal, acidotic, or alkalotic?
So this you kind of already know the answer. pH should be 7.35 to 7.45. So they're either left of that, which is acidic, or right of that, which is basic. Now, when you look at the word arterial blood gas, you get this from your arteries, right? Unlike, when you get blood, you get it from your veins. This is from your arteries because your arteries are oxygenated. So one of the things you're going to see here is PO2, which is partial pressure of oxygen, right? O2 sat is the oxygen saturation, meaning how many molecules of oxygen are actually sitting in your red blood cell at the time. We already know what carbon dioxide is, bicarbonate, HCO3, and these other items. So let's continue.
Step number 2 we ask, is the CO2 normal, acidotic, or alkalotic? And step number 3, we're going to ask, is the bicarb normal, acidotic, or alkalotic? Next, we're going to look at the CO2 and the bicarb and determine which one of those matches the pH. So in other words, we're looking for the ones that have the same interpretation. If the pH was acidotic and the bicarb is acidotic, those are the two that match. After we've made that determination, and by the way, that tells...
You can also see here, so if the CO2 matches, that means you have what? A respiratory issue. If the HCO3 matches, that means it's what? It's potentially a metabolic. So there you already are, you could see how diagnoses are made. There are steps. It's not like, maybe if you've seen or seen TV or you watch doctors at work, it's not a guessing game. It looks like sometimes it feels like we're guessing, but we're actually, if you see here, we're running a protocol, right? A protocol that has to be repeated the same exact way for every single patient. Okay. So that's actually what we're doing when we medically manage somebody. We're following a very strict set of rules that are dictated by anatomy and physiology.
About the primary imbalance that our patient has. Next, we move on and we look at the CO2 and bicarb to see if one goes the opposite direction. If one goes in the opposite direction, that is called compensation. So we're going to assess that too. Then lastly, we look at the PO2 and the O2 saturation to help to tell us about the patient's oxygenation. Now, I briefly mentioned this concept of compensation. What compensation refers to is that the body wants to maintain a pH of 7.40 all the time. So we want to have this normal pH flow.
And remember that's 7.35 to 7.45. So 7.4 is a good round number in between.
Around in the bloodstream, we don't want our pH to be high or low. So if something happens, for example, if the lungs are causing this CO2 to become low, then the kidneys are going to have to kick in as a compensatory mechanism and try to balance out our pH. So there's a normal balancing act that's occurring here between the lung and the kidney all the time in
which
order
is essentially
to maintain a normal
homeostasis.
pH.
Now, you can easily see how this gets complicated if my patient has any lower respiratory tract infection and or any cardiac problems. You could see how that's going to mess up this part of the equation. You could see here if my patient is diabetic or has any nephrology issues, that's going to mess up this part of the compensatory equation as well. And therefore, if either situation exists, we can now see that there's going to be effects on the pH and its compensatory mechanisms.
Compensation by the lung, as you may imagine, could be very rapid. All you have to do is breathe faster or breathe slower to get rid of more CO2 or to retain more CO2. On the other hand, the bicarb is a little bit more difficult because in order to maintain, to change your bicarb, we're going to have to either retain more bicarb by the kidney or we're going to have to dump off more hydrogen ions. So we need to have some time in order to do that. It takes about 8 to 24 hours to get compensation out of the kidney, whereas it can take just a matter of minutes to get compensation out of the lung. Now, here's the normal values we see on our arterial blood gas. A pH is 7.35 to 7.45. Notice that very
So these are
tight
numbers that
range,
you can
right
start
around
memorizing.
7.4. By the way, as you're looking at lab values,
Not really for
just
this
in
class,
general,
but for
the
future
wider
classes.
the range is, the more likely it is the patient can tolerate being outside the range. The more narrow the range is, the less likely the patient can tolerate being outside the range. So, for example, in this case, 7.35 to 7.45, we could have somebody who's at a 7.3. Okay, they're only 0.05 out of the range, yet they could be very symptomatic. On the other hand, look at the CO2. CO2 is 35 to 45. You might be able to remember this easily by just remembering it's the same last two numbers as the pH. But the CO2 is normal range is 35 to 45. So somebody who has a CO2 of 30 is probably not going to be very symptomatic because there is such a wide range in the CO2. You see the difference between those? The tighter the range, the more likely somebody's going to be symptomatic, even with a little bit of a difference. But the wider the range, the less likely the patient's going to have symptoms with just a tiny little change in the range.
And that's not necessarily true. I've had patients who were so far off and they were asymptomatic. And I also had other patients that were just a little bit off and they were very symptomatic. It has a lot to do with how strong my patient's chemistry is, how strong my patient's lungs, and how strong my patient's kidneys are. That's what is more of a predictor. But you could see here that also O2 sat, I don't agree with that number. O2 saturation has to be at least 97% and higher. I had pneumonia and I had a 96% O2 sat. So, but again, I'm not elderly. I'm in relative health and tolerable shape. Again, it's a patient-to-patient basis, but you could see how we can use numbers to kind of predict what's going to happen.
Normal is 80 to 100. Okay, PO2 is the amount of oxygen that's dissolved in the blood. Right? It's not what you get on a pulse ox. And then your bicarb, normal is 22 to 26. Our oxygen saturation, normal, is going to be 95 to 100%. So here's what happens when the values become abnormal. If our pH is less than 7.35, the patient will develop acidosis. If the pH is greater than 7.45, we have alkalosis. If your patient has a CO2 less than 35, they have alkalosis.
Now this is
and
obvious.
Greater than 45, they have acidosis. This is interesting, isn't it? When you take a look at these values right here, you'll notice that the CO2 goes the opposite direction of the pH. This is why we don't want to talk about.
Because we already know why CO2 goes the opposite direction, because of the compensatory. It's a compensatory mechanism, so it's going to be opposite.
Values being high or low, but we want to make the interpretation of the value instead. One way to remember this relationship between our CO2 and our bicarb and our pH is to remember the acronym ROME, R-O-M-E. ROME stands for respiratory opposite, metabolic equal. Respiratory opposite, metabolic equal. So the respiratory is opposite of the pH. The metabolic system, the bicarb, is equal. It does the same thing. In other words, when the bicarb is less than 22, we have acidosis. Greater than 26, we have alkalosis. When our PO2 is less than 80, we have hypoxemia. Greater than 100 only happens when somebody is on oxygen therapy. So we're going to anticipate that the person is on oxygen therapy if our O2 is greater than 100. Oxygen saturation less than 95% indicates hypoxemia. And of course, you can't have a higher than 100% oxygen saturation. Here are the normal values again, and if you'd like to stop the video at this point just to have the normal values up on your screen, you can do so, and then use the 6 Easy Steps to ABG Analysis ebook to be able to answer the question.
All right. Well, this is where we stop because the rest of this video is pertaining more towards nursing and ABG. But but we're gonna just for laughs. Let's look over one example where you could see that medical management and all of this stuff, it's not a mystery. It's just a set of steps based on science that you should perform. But once students see numbers and opposites, increase versus decrease, they start getting nervous, and they start, you know what happens when you're nervous? You start picking the opposite thing. And that's why Dr. Bettini, she fails a whole bunch of people because number one, this is something that just like any skill set should be practiced. Okay, so so a nice thing that you could do there's a whole ton of these videos because again, this is one of these high valued topics that are on your future NCLEX, and there's tons of videos and practice sessions regarding this where they give you the problem and then you could try to interpret it and then see if you got the right answer. And just like math or any word problem, you always have to define your terms and know your protocol on what to do next. So let's look at one of his examples and then apply it to that protocol, the 6 steps.
These scenarios that are listed in there. We're going to practice a scenario here in just a moment, but these normal values may help you in order to interpret the values that are in the ebook. Well, hopefully you got some value out of looking at those values and interpreting them with the ebook. But I would also like to talk to you about a couple more components that we see with an arterial blood gas. So the blood gas may be drawn and it comes back.
Well, now they're getting into some technical. I just want to get to an example.
Acid-base imbalance. What it does is it measures monitors and it assesses the right amount of base because it means instead that we have acidosis. So if we have a negative number,
where
we would look at an anion gap. An anion gap looks at our positive ions. So let's take a look at an example here of an arterial blood gas. Here we have Mr. Pina. He's 72 years old. He has a diagnosis of congestive heart failure. His history is heart failure, renal failure, hypertension. Found this morning
so
in
we
a
see now
pulmonary arrest.
He has a renal problem and a breathing problem secondary to his heart problem.
He has a CO2 of 62, bicarb of 14, PO2 of 80, oxygen saturation 89%, base excess minus 11, and an
Now, don't worry about anion gap and base excess. So you can now see, you can easily, now you know your normal values. What's wrong? pH right off the top is what? Is it acidotic or alkalotic, or acidotic or basic? With a pH of 6.98. My patient is, survey says, a little bit on the acid side, right? So, of course, PCO2 will be increased because it's the compensatory mechanism for the pH being acidotic, right? And my bicarb is also what? If you look at my bicarb, it's also low. PO2, very low. O2 sat, very low. So you can see now that this is my patient, right? When we look at the rule says, what's my pH? That's the primary issue. So the pH is what? Acidotic. And it goes, if you see the compensatory mechanism in play, now you could see that my patient has respiratory acidosis secondary to congestive heart failure and chronic renal failure, right? And you could see its effects on the O2 sat. So again, just wanted to give you an overview. I don't want to get into ABGs because that's Dr. Bettini's job, right? And but it's a nice thing to know that the things that you are currently studying are actually relevant to what you'll be doing and what you'll be looking at in the real world. And of course, lesson 9, case of respiratory distress. Open that up, and I remember it had a ton of stuff. No, not too bad.
Since you're on the case study, can you look at, for the case study questions, question 3, did you want us to go ahead and answer that still, since it's saying, like, referring to question 7 from your homework?
Yeah, just answer the question, because if you look at 3, explain the difference between acid base, right? You can answer that. You don't need to look at.
Well, no, it's the next question 3 and the actual case study questions. Those are the pre-case study questions.
Referring to question 7 from the homework.
Yeah.
Just draw, what conclusions can you draw from the result of your patient's ABG?
Okay.
And make it basic. You don't have to get into like AG and all that stuff, you know?
Mhm.
Again, I just want, actually, you know what? I hope everyone's watching this. Just do, just do the initial 1 through 12, because this stuff is getting into numbers, the case question.
Just so the pre-case
pre-case,
study questions or
yeah.
the actual case study
Just do,
questions?
everybody, if you're watching this recording, just do the pre-case questions. And also, I want you guys to have time to do your, to prep for your other class and your other finals. Yeah, I'll give you guys a break, because I don't want to get into, because that's full-blown set of lectures doing ABG. Yeah, just do the pre-case, first 12 or so. That's better.
Mhm.
Hey, Manhattan Community College. I taught for them once. All right. So, hey, I also used to do transport for Jamaica Hospital before it got bought up. Oh, my Lord. Bad place.
Mhm.
Back then in the 80s, it was bad news. All right. Enough side talk. It goes, is it clear? Everything we need to do? You need to do this discussion case. I mean, there's discussion, of course. This case only the pre-case questions, right? I don't want to get too involved, right?
Mhm.
And the task, which is most probably what? It's
Concept.
probably just another concept map. And
Mhm.
remember, I'm telling you, because those concept maps, remember, like I said, knowing and understanding protocol, what's connected to what goes next. The concept maps may seem like busy work, but it's giving you a skill set on how to start looking at things like a protocol, how to start looking at things like a map of, this is where I go, then this down this block, and down that block, and then down another block, so that you're relating all the information instead of just having separate bits of information. Because if you relate everything, then you could see the big picture. You see the big picture, then your life as a clinician is much, much easier. All right.
Alrighty.
Well, if that being said, no lecture. Again, I have to repeat, no lecture next week, right? And this is currently week 9. Next week is week 10. By Saturday, 12 noon, I have to get grades in. So by 11:30-ish, everything is going to essentially get closed down. So don't be one of those people calling me 11:29, because I have to tell you I can't do anything for you. Okay?
All right. Yep.
So that's just my public service announcement, because there's always one in every class that asks. All right.
All right.
Everything's all good. Have a good one, and I'll see you when I see you. All right.
All right.
Signing off.